In section 3.9, we learn about linear approximations and also differentials. So you already know that when you look at a function graphed with its tangent line, the tangent line and the function are very close together when you're close to the point of tangency. And actually, another way to say that is that a differentiable function is locally linear. So if you, for example, have a function and its tangent line graphed together in your calculator, and then you use the zoom in button, the further you zoom in, the less and less you'll be able to tell the function and the tangent line apart. And eventually, if you zoom in far enough, it just looks like one graph. You can't tell the difference. And they mention here figure 2 in section 2.6, if anybody's interested to go back and look at that on page 136. So the thing is that we're going to use this idea of linear approximation to calculate approximate function values. So we'll use the tangent line to make our calculation as opposed to the function. Okay, so the idea is we're going to use a value on the tangent line to approximate or estimate a value on the function. Now, as you can see in the picture, and I'll mark that up in a minute, this is going to work well if we stay close to the point of tangency. So in the picture here in figure 1, we have, whoops, put that on a little too soon. We have our input value of A, right? This point AF of A, we call that the point of interest, right? Which I hesitate to abbreviate anymore so we don't mix it up with point of inflection. But you can see that there's a portion of the picture where we really can't tell the blue graph, which is the function. Let me try to make this a little bit better. And the pink graph, which is the tangent line, we really can't tell them apart. They're very overlapping, right? So visually, we can't tell the function and the tangent line apart. On some interval around x equal a. And that's what I've depicted with my little parentheses up there. And this is what we mean when we say we talk about local linearity. In other words, locally, meaning in some interval around x equal a, the function looks just like a line. It looks like the tangent line. All right, now, right, and that's, so what it says at the top of the second page here, we use the tangent line at the point of tangency as an approximation to the function y equal f of x. So we already know the equation of the tangent line. It's written there, right? We've seen that before. And let me just again emphasize, that's what we just got done saying. If we stick close to x equal a, the further away we get from a, the further the tangent line and the function get from each other. Okay, so what we have in this box, equation 1, we have f of x, that's the actual function value, and then we have f of a plus f prime of a times x minus a. I don't know if you recognize that. That's the tangent line value. And what this is saying is that they will be approximately equal on some interval around x equal a. And it tells us here that that approximation is called the linear approximation, or the tangent line approximation of f at a. Right? So again, now we're labeling that tangent line equation with capital L for line. That's also called the linearization of f at a. Right? So again, let's just remember where this comes from. To find the equation of the tangent line, we need a point and we need a slope. Oops, equation. To find the equation of the tangent line, we need a point and a slope. Now when we're creating the tangent line equation, we use the point-slope form of a line. Right, because we have a point and a slope. That is y minus y1 equals m times x minus x1, so that's the point-slope form of a line. So the point, which in that equation is designated x1, y1, is in this tangent line equation the point of tangency, or the point of interest, or the tangent point, that is a, f of a. And then the slope, m, is the derivative, right? The slope of the tangent line is the derivative at x equal a, right? So we evaluate the derivative at the point of tangency, and that is the slope of the tangent line. So if we put those two things together, then the equation of the tangent line, and again, this has been done many times, I'm just reminding you. So we do y minus y1, which is f of a, equals m, that's f prime of a, times x minus x1, and x1 is a. And of course, what many of you already do right from the get-go is add the f of a over to the right-hand side. Now, we've been used to putting it at the end, but in fact, what your book is doing here is just putting it at the beginning of the right side of the equal sign. Doesn't really matter one way or the other, right? And so again, this is the tangent line equation. It's here. It's also here. And it's also here. Now, the difference in equation 1 is that approximately symbol, right? So the right-hand side is the tangent line equation. The left-hand side is not actually designating the tangent line, it's designating the function, right? So this one is a little different than the other two. In equation 2, L of x designates I'm on the tangent line. Equation 1 says, well, I'm on the tangent line on the right-hand side, and I'm using that to approximate being on the function on the left-hand side. Now, I am asking you to read here example 1 and example 2, but of course, in this distance learning environment, maybe you'd like to do even more reading than that.